Okay, so we're in the example section now. And as I do the example, what I'm going to indicate over here is that I want to go through what we just did in lecture. So we covered the integral test, you know, we covered, you know, that's from the past lecture, test for divergence, not a bad thing to be doing. We covered the comparison test. We covered the integral test. We covered the comparison test, comparison test, comparison test, comparison test, comparison test. We covered the limit comparison test. So what we're doing is we're trying to, confirm that we did this, right? That's all we're trying to do. Some of these problems are more difficult than others, but I want to go through it with you. All right. So this comparison test, yada, 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 comparison test. All right. So after we go through that, certainly going through that at the whiteboard, then, a chance for you to try. You got to try. All right. So let me go to the whiteboard and give me a second to start a new share. And give me a second over here. All right, I think we're at the whiteboard now. So as I'm doing this over here, when I'm doing it, certainly we hope your work on exams would be readable. Certainly I typed this up for you. I'm not expecting on exams you type, but I'm going to look at this problem over here. And, one thing I would do, probably just from the get-go, just this from the get-go, I would look at it and, this is definitely a positive term series. All right, so it's positive terms. Let me go through that with you. So if you start with 1, what do you get? 2 minus 1 is 2, and you square it positive. 2 would give you, I hope you start to realize that the only place this becomes 0 is a half, and that's never there. So I'm always saying that you're squaring some positive number. It's going to be positive. Every term's positive. All right. So number 1, I know it's a positive term series. So I'd say, what test am I going to use? Well, the first thing I would probably do is I would look at the limit as n goes to infinity of an. And what's an? It's this over here. Well, unfortunately, this is 0. So this is no help to me. Doesn't say anything about the series. All right. I was hoping it was going to be a non-zero number, but that's 0. That doesn't help me. So then the question comes is, what do you want to do? Well, there's many things you could do, but I want to start off with the integral test. So the first thing I do is I want to write down a function that looks like that. That would be 2x minus 1 squared. Now, by the way, this is continuous everywhere except at a half. So I'm going to say it's definitely continuous on the interval from 1 to infinity. I can definitely say that. What's the next thing I could say? Continuous, is it positive? I can definitely say this is always positive, but certainly on 1 to infinity. So remember CPD, right? I see it decreasing. I hope you realize as I do this over here, looking at it, it's definitely decreasing on 1 to infinity. Now, if you're really retentive, what you could do, I'll write this down for you. You could differentiate, right? What do you get over there? Minus 6, 2x minus 1 to the minus 3 times 2. Let's put this over here. This would be minus 12 over 2x minus 1 cubed. And I'm going to start at 1. Remember, the only place that this thing is has a problem is at a half, and 1 forward, no problems. This will always be negative. Take any test point, take 2. What do you get? Minus 12 over some positive number. Well, it's always negative. What does that mean? It's always decreasing. So I'm pretty much convinced of this. All right. So I want to use the integral test. And how do I do that? Well, I know it's continuous positive decreasing. And I'll look at this over here. I'm going to go 1 to infinity, 3, 2x minus 1 squared dx. Well, Again, if this is an exam question, you want to put as much work down as possible. Let me just see if I can do the integration without doing a limit. So I'm going to say 3 comes out. Yeah, I'll put 3 out. You get 1 over 2x minus 1 squared dx. I'd probably use u substitution, right? Was that going to be 2 dx? I'm sorry, I get to the u first. I'm sorry. U is equal to 2x minus 1. Du is 2 dx. Let me write this in. This is 3. This is 1. This would be u squared. What's dx equal to? Well, it's 1/2 of a du. So what's this going to be? 3 halves, u to the minus 2, u to the minus 1 over minus 1 plus c. I think I can do it. Let's write this down now. So what do you get over here? Oh boy, gotta write it down. So it's going to be, let's see, minus 3 halves, limit a goes to infinity. And what do you get over there? You get 1 over 2x minus 1. Limit integration would be 1 to a. Let's write that down. You get minus 3 halves, limit a goes to infinity. This would be 1 over 2a minus 1. And then you get minus 1 over 1. That's not so bad. And what does that give you? It's work. I know it's work. So the first guy is going to be 0. A goes to infinity. Then you get minus 1/3 times minus 1 over 1, which turns out to be 1/3. All right, let's look at our k. Oh, before I do that, my conclusion is the series converges. So this series, my conclusion by using the integral test is that this series converges. All right, let's see if we got the right answer. And I think I made a mistake somewhere. Oh, I'm sorry. I don't know how that happened. I'm going to erase this over here. And I really don't know how it happened. That's minus 3 over 2. And I'll erase this over here. So I don't know how that happened. Maybe not thinking, right? So the 3 over 2, we got that. All right, let's look at this one over here. And I'm looking at it, and I'm going to say, number 2, it's definitely a positive term series. So it's a positive term. So I'm always hoping that first test works out. Let's take a look at that. And that's the test for diversion. So I'm going to go n goes to infinity. And what do you get? N over n plus 1. Well, that limit just couldn't get any easier. It's 1 over 1, which is 1. So I know this series diverges. What am I using? The test for divergence. Super simple. No need to do any more work on that guy over there. All right, let's do number 3. And number 3, there's many things you can do. And I'm going to say you could definitely use the integral test if you want to, but I'm going to use the comparison test. So let's write this down for you. So I'm going to use the comparison test. What am I saying? This is a positive term series. How do I know that? Look at it. It's 3 divided by n squared. It's positive term. All right. So what's a good comparison for this? And I have to look at it. I'll be honest with you. I have to look at it. So I'm going to say a good comparison for this would be a p-series. And the p-series I want to use is one that looks like that. So I'm going to say this would be 1 over n squared. What do I know about this? This is a convergent p-series. Again, the n is great, the p is greater than 1. Now, what I'm going to say over here, if this is true, then 3 times that would be true. And we have properties of convergent series. This is also convergent, by the way, just a multiple of convergent series. And what is this equal to? N equals 1 to infinity, 3 over n squared. So we're going to do comparison test. So to do this comparison test, what am I trying to show? I'm trying to show that this guy here, this term here, is somehow related to this term over here. And what are we trying to show? Well, if it's convergent, we want to show this. I want to show it. All right, I want to show that. Oh boy, I guess I hope you realize that everything's positive number, which makes it super simple for me to do. What do you get? 3n squared. 3n squared plus 12. And this would be this. This is always true. All right. So what we conclude, this converges. And what do we use? Comparison test. Let's look what I did over here. I wrote that down, indicating the comparison we're using. Convergent P series converges. All right. Let's go to the next one. And I'm looking at this one over here. It looks nightmarish to me. And I'll be honest with you, the reason it looks nightmarish to me is that, yeah, it really does. But I'm still going to do the same thing. I'm going to do limit as n goes to infinity, n plus 2 over n, n 2 to the n. I got to do, I'm hopeful, right? So we get limit, n goes to infinity. Well, you're going to get two terms, right? So n over n, so it's 1 over 2n, plus this would be 1 over n. Well, you know what? This didn't help me at all. The reason that limit's 0. That's sort of a nightmare for me. So I was hoping that would be, doable. Now I'm kind of looking at it, and when I'm looking at something, sometimes I struggle with it, and I say, what the hell do they want me to do with that? And my understanding of this over here is that I'm going to say this really doesn't look like it compares to either. Well, I guess it really does. I guess if I looked at these two guys over here, but that's a problem for me. I'll be honest with you, because one of those conversion, one is divergence. That's mixing things together. That's beyond my skill set at this point. So I'm going to say I'm going to be looking at not a comparison test because I don't know what to compare it with. Kind of mixing things together, right? Now I might have suspicions about it. I'll tell you why I have suspicion about it. Looking at this one over here, the series there would converge, but then this one here blows up. So I have suspicions, high suspicions that this thing's going to blow up. All right. But I want to do something. I want to use what's called an integral test. And I'm going to put this down here. It's definitely a positive term series. Again, I want to make sure you're looking at that and know what I mean by that. The end's a positive number. The top is always positive. The bottom is always positive. So I'm going to write this over here. F of x equals x plus 2 to the x over x to the x. By the way, I don't want to differentiate that. I'm going to look at it carefully though. It's 1 over 2 to the x plus 1 over x. All right, that doesn't look too bad to me, actually. Make sure I did that right. That looks okay to me. All right, so I'm going to say that f of x is certainly positive on the interval from 1 to infinity. Just look at it right over here. The next thing I'm going to say, it's continuous. The only place where it discontinuous would be at a 0. So I'm going to say 1 to infinity. I'm also going to say it's decreasing. So how could you say that? Just look at it. What happens? Every x we take above the 1, those terms are getting smaller and smaller and smaller. So it's decreasing on 1 to infinity. Now here comes my problem. I got to integrate it. And what's that integration going to be? 1 to infinity. And I'm going to write down, I'm writing this over here. I'm going to put 1 over x plus 1 over 2x dx. All right. I want to briefly go through this with you. And I know it's difficult. You may not be able to remember, and that's fine. But I'm worried about, I know the antiderivative for 1 over x, but I can't remember the antiderivative for 1 over 2x. So I got to remind myself. It's going to be y equals 2 to the minus x. And I'm going to take the log of both sides because I can't differentiate that, right? what would they give you? Minus x ln2, and you would get y, right, equals e to the minus x. I'm sorry. Let me go backwards because maybe I went too quick for myself as well. So I took the log of both sides. And what I want to do is differentiate. I apologize. I forgot I was doing something. I was rewriting it. No, I want to differentiate it. So what do you get over here? 1 over y dy dx. By the way, so this is why I want to differentiate. I can't integrate unless I can differentiate. And that's so true. That's why we teach differentiation first. What do you have here? Minus natural log of 2. So dy dx equals y. What's y? Oh, that's not so bad. So it's minus ln2 times y, which is this. All right, that's what dy dx is. So I got to think about this now, right? So I'm going to write this down now. I'm going to write this as a limit. It's tough though, I know that. A goes to infinity, 1 to a, 1 over x plus 1 over 2 to the x dx equals limit a goes to infinity, the natural log, absolute value of x. We'll do that later, don't worry. I got to worry about this thing over here. And, what would differentiate to that? Let me write down something I think is going to work out nicely. So I can put this over here, 1, let's see, minus ln2, so that'd be plus, right? I'm sorry, no, I got the minus in it, I'm sorry. It's always tough to think, right? I'm going to check it though. Don't worry about that. I want to see if that's true. If you differentiate this, let me point out what I mean by that. You get this. That's something I know from Calc 1, right? If you differentiate this, I'd get minus 1 over natural log of 2. Derivative of this thing over here is going to be, wow, that worked out beautifully. It did, all right? That's why I went through so much work over here, so I could do that over there. Someone says, could you just remember that? Maybe, not me. I'm not very good at remembering anything. So I'm going to see if I can do the limit now. And unfortunately, looking at this guy over here, it's a little complicated for me. I'm going to write it down for you. And what do you get over here? Well, z goes to infinity. This goes to infinity, and this goes to 0. This is infinite. All right, so I forgot why I did that. The reason you did that was you want to see if the original series converged. Right now, I know by the integral test, this series diverges. This diverges. Let me use the integral test. Let me just look at my work, by the way. When I do that, I want you to look at your work as well. What are we looking at? The work that's being provided to you over here. Now, someone says you didn't put all the work down there. It's true. But if you think I could put that work on my paper that I put down over here, which typically a textbook would have down, the side work needs to be done. I couldn't have written that down without the side work, and I did the side work for you. All right, let's look at number 5. And number 5, I know they're using the integral test. I see that, and I don't mind you doing that. But what I want to do is I want to use a comparison test. And the comparison test I'm going to use the LCT. I think it's easier. So what am I going to do? This is definitely a positive term series. And I'm going to compare it to another series. What series am I going to compare it to? Well, look at the top. Top's roughly n. The bottom's roughly n squared. So I'm going to compare it to 1 over n. And this would be n equals 1 to infinity. This is a divergent P series. Again, I'm using LCT. What do I have to do? Whoops, I'll put it over here. I got to do this. The limit as n goes to infinity. I'm going to take this. This is n plus 1 n squared plus 2n plus 2 and divide it by 1 over n, which is like multiplying by n over 1. And again, I'm using limit comparison because I find it easier to deal with that. Integrations for me are always difficult. Now, by the way, I noticed an easy limit. You don't have to do the work I'm going to put down now, but I do want to put the work down for the students that need it. Divide through by n squared. This would be 1 plus 1 over n. This would be 1 plus 2 over n plus 2 over n squared, and that limits 1. Is that a finite positive number? Yes. So what's my conclusion? Well, if this series diverges, this series would also diverge, and that's stated right over here. All right, let's look at number 6. And I'm going to look at it. And number 6 is, and I'll tell you what test I'm going to be using. N equals 1 to infinity, n minus 1, n cubed plus 3. I'm going to compare this guy to this one. By the way, this is a, certainly the first term is 0. I'm not too worried about that, by the way, but every term after that is positive. What do I mean by 2 gives you a positive number, 3 gives you a positive number, yada, yada, yada. But I do realize that 1 is 0, but that's okay. It's not gonna change the problem at all. And I'm gonna say this compares nicely to this. And someone says, why do you say that? Well, look at the top. For large n, the top looks sort of like n, and for large n, the bottom looks like n cubed, and n divided by n cubed sort of looks like this over here. So I'm going to say this is a good comparison. And what is this over here? This is a convergent P series. Well, I'm going to use the limit comparison test because I find it easy. So what do you get over here? Limit n goes to infinity, n minus 1, n cubed plus 3. I'm going to divide by 1 over n squared, which is like multiplying by n squared over 1. And again, you can get better at this over time. Don't feel it's a speed contest, though. This would be n cubed minus n squared. The bottom is n cubed plus 3. And for the students that need, I'll put the work down. This is limit. N goes to infinity. I am going to divide by n cubed. And what do you get? 1 minus 1 over n. This would be 1 plus 3 over n cubed. That limit's pretty easy to do. You get 1. Finite positive number. What's my conclusion? This is convergent. And what did we use? The LCT. All right. Now, certainly, they said converges. It does say use one of the comparisons. I did do that. All right. So use one of the comparison tests over here. Again, I'm going to use LCT. Right. So this is, I think I just did number 6, right? Yeah. Let me go to number 7. So number 7, this is the sum, n equals 1 to infinity, and this is 6n cubed, I'm sorry, n squared, sorry about that, plus 1, and 2n cubed minus 1. And I'm going to say this compares with, now looking at it, it compares with, I'm going to say 1 over n squared, and I'll go through, 1 over n. Before I move forward, though, I want to claim that this is it's definitely a positive term series. There's no doubt about that. All right. And what am I going to do now? Well, I guess I'm going to do the LCT. It's easy for me, right? What's this one over here? A divergent P series. All right. Let's take a look at this. Limit n goes to infinity. 6n squared plus 1, 2n cubed minus 1 times, well, that's going to be, I'm dividing by 1 over n, so it's times n over 1. Let's go through this. Again, for the students that do this quickly, that's fine. I just want to accommodate everyone. That's going to be 6n cubed plus n. On the bottom, you would get 2n cubed. That's a cube, minus 1. I'm going to divide by the highest degree variable. That's what you were taught to do in Math 119, by the way. That's 6 plus 1 over n squared, because the highest degree variable is n cubed. And then you get 2 minus 1 over n cubed. And this would give you 6 over 2, which is 3. Surely that's a finite number. What do I know about this over here? If this diverges, this one diverges. Okay. Let's take a look at that. And I'll go to the next page. And it says diverges. They said they use a harmonic series. Harmonic series is a P series. Okay. So let's look at this one over here. And, I'm going to use one of the comparison tests. And I'm going to say, I don't know. Let's look at it. And I'm going to say, what does it compare with? And I'll write this over here. This is the sum n equals 1 to infinity and 1 over 2 to the n plus 1. I'm going to say this definitely is not a P series comparison. I'm going to look at geometric. And I'm going to say n equals 1. By the way, this is a positive term series. I probably said it enough times. I'm going to say this looks like a convergent geometric series. This is convergent geometric series. Definitely convergent. I'm going to use a comparison test. I don't want to do the limit. So what do you do over here? I want to show I want to point out what we're talking about. This guy's sum is finite, and you could actually get its sum, by the way. This guy's sum I want to show is smaller than this one over here. So I want to show the terms are smaller. How am I going to do that? Well, everything is positive, makes these things super simple to solve. And what is this going to be? 1 is greater than 0, which is certainly true. So what do I use? Comparison test. What's my conclusion? This is convergent. Let's take a look. And they converges and they use a geometric series like I did for comparison. All right, let me look at number 9. Number 9 looks like a nightmare to me. It's got the natural log in it. And I'm always worried about that. So I'll put 9 in the side for you. And that's a sum, n equals 1 to infinity and ln n over n. So what I'm going to do over here is, again, certainly in the notes, I might do one thing. In class, I might do another. On Tuesday or Thursday, I might do something completely different. You know that? It's going to happen. Let's take a look at that. So is it positive term? So looking at natural log of 1, well, that would be 0. But once I pass that 0 term, it's always going to be a positive number. All right, always going to be a positive number. All right. So what I'm going to use is I'm going to use an integral test. And the reason for that is I think I see something. So I'm going to go through it with you. And what I want to go through with you, I definitely want to say that this is definitely continuous on the interval from 1 to infinity. All right. Now, is it positive? I'm going to claim it's positive from 1 to infinity. If you think about it, the number on bottom is always a positive number, 1 to infinity. The number on top, the natural log of x, well, if we're starting at 1, natural log of 1 equals 0. All right. So, when I say positive, it's not, there's no negative terms in it. All right. So if you thought about the log function, once you get to 1, it goes positive after that. All right. All right. So 1 to infinity. All right. Let me just erase this over here. Let me see if it's decreasing. How would I do that? Let's take a look. Square the bottom. Bring the bottom to the top. Derivative of the top minus the top times the derivative of the bottom, which is x. I'm sorry, which is 1. Sorry about that. What do you get over here? 1 minus the natural log of x over x squared. Geez. Where does that take on a 0? At e. I hope you know e is between 2 and 3. I got troubles on my hand now. So I need to pick a number after e. And what's a good number after e? Like 3, and this would be negative. So I need to rewrite this problem, and this might seem painful to you, as n equals 1. I'm going to go to 3 first. I'll put this over here. And that's going to be ln n over n plus, now I'm going to start at n equals 4 and go off to infinity. All right, so I'm going to claim over here, I'm changing my tune to 4. So let me erase all that little work on the side. Maybe not. I'll put this down. I'm going to say it's decreasing on the interval from 4 to infinity. By the way, someone says, why'd you pick the 4? You could have picked the 3. I just like the 4 for some reason today. All right. So what do I need to do? I need to do an integral. All right. By the way, this thing here is a finite number. I can add, the term where it's 1, 2, and 3. That's not a problem. I'm worried about this. Let's write this down. So it's going to be 4. Again, I'm doing this now. What am I doing? I'm doing the integral test. Going to 4 to infinity, ln x over x dx. Someone says, why'd you choose the integral test? It's so much more difficult. I don't know. Shake it up a little bit. Let me do a side work over here. ln x over x dx. U is equal to ln x. du is 1 over x dx. Gee, this just couldn't get any easier. What do you get over there? Well, let's see, you get u du, like I did it right over here. That would be u squared over 2 plus c. I am ready to go. What do you get over here? Let's write this down for you. The limit a goes to infinity. And that's going to be, let's see, what's u? ln x, right? So it's going to be ln x squared over 2. I think I did it right there. And that's going to be evaluated from 4 to infinity. I'm sorry, to a. I'm sorry. Let's write that down. Limit a goes to infinity. And what do you have here? Natural log of a, quantity squared, over 2 minus the natural log of 2 squared over 2. And what's this giving? Infinity. So what do I now know? By integral test, I know that this thing diverges. If this diverges, this certainly diverges. All right, finite number with diversion. Let's go back to our key. This is number 9. And let's take a look at that. Diverges. All right. By the way, they use the harmonic series for comparison. That might be tough for some students to deal with. All right. All right, let's do number 10. And number 10 looks like a nightmare. All right, let's write this down for you. This is the sum. N equals 1 to infinity. 2n squared plus 3n. Top is definitely positive. And the bottom is definitely positive. Everything's positive. All right. So I'm looking at it and, certainly I'm always saying, do that limit test, blah, blah, blah. I'm looking at it. The limit's not going to help me out at all. So I'm going to look for a comparison. I'm looking at it. And the degree at the top, I want to point out, is n squared. When I say that, that's the most powerful term, is the n squared guy. I'm not worried about the coefficient. On the bottom, it's actually n to the 5/2. Well, if I did this, if I reduce it, it would be n. It's 5/2, right? Yeah, 5/2. What's 5/2 minus 2? Is 1/2, right? So what I'm going to use, I'm going to say for comparison purposes, I'm going to use this. And what do I know about this? This is a divergent P series. And what I'm going to do, I'm going to use the limit comparison test. Let's write down limit n goes to infinity. 2n squared plus 3n over the root 5 plus n to the 5th times. I'm really dividing by 1 over n squared, which is like multiplying by the root of n over 1. All right, let's multiply it out. And I know it's tough. Well, it's going to be 2n. Let's see, that would be 5 halves, right? Plus 3 times n to the 3 halves. And on the bottom, you get this nightmare. Well, what I'm going to do is I'm going to divide top and bottom by the highest degree variable, which is this. Let me put that down for you. That would be 2 plus 3. Well, let's see, 3 halves, 5 halves, 2 halves, which is 1. Boy, that was easy. And now I got to do this guy over here, which is going to be, and I'll write this over here for you. I'm taking this and dividing by this. So it's going to be 5 over n5. By the way, that's a 5 there, sorry. And that would be plus 1, right? And I realize what some students are. It's too much work for me. 2 over root 1, which is 1, which is 2. So what do I do? I just can't remember what I've done, right? So the limit's finite, it's 2, right? So if this diverges, all right? So let's see what we did over here. I'm going to read it through for you. Which problem are we doing over here? I guess we're doing this one. Yeah, it diverges. What do? We use the p-series for comparison. All right, this one says use a limit comparison test. I'll do as told. I like the limit comparison test, by the way. It kind of prevents me from doing inequality. Let's just look at it real quick. I'm going to say a good comparison for this one over here would be n equals 1 to infinity. The degree on the top looks like degree 2, degree on the bottom, degree 4. So I'm going to say 1 over n squared is a good comparison. This is convergent, p-series. All right, I'm sorry, give me 1 second, okay?
I didn't get that. Could you try again?
So convergent p-series, that was Siri coming into the picture there. Sorry about that. It's convergent p-series. And let's take a look. Let's see what time I got here. Yeah, we're all right. So let's do it. Let's do the limit comparison test, all right? You know what? It's written down. I'm not going to write down for you. Actually, is it written down? No, it's not written down. I'll write it down for you. Limit n goes to infinity. I'll put the n squared plus 6. And on bottom, you get n4. Whoops. Siri threw me off there. I'm going to divide by 1 over n squared. It's like multiplying n squared over 1. What does this give me? Limit. That's an infinity. N goes to infinity. What do you get on top? N4 plus 6n squared. On bottom, you get n4 minus 2n plus 3. Well, I've done a number of limits right now, and that looks pretty easy. If you divide by n4, you get 1 over 1, so 1. So what do I know about this over here? This converges, all right? And this is indicated in your notes, I believe. Let me see. Let me on the next page, hopefully I say the answer. Yeah, converges, all right? Okay, number 12, all right, number 12. Again, I'm looking at it, and I'm really, I'd be at a loss for finding a good comparison for this one over here, but I'm going to write down what they've given me. And sine 1 over n. Now, what I'm going to say, and again, this might seem strange to you, but you certainly know a lot about the sine function. And the sine function, you know, sort of looks like this. Now, I'm not saying it's easy for you, by the way, but someone says, why did you draw it there? Well, if n goes towards infinity, I'm really looking at this region in over here. Sorry about that. So what I'm going to say is that it really looks just like, you know, like for example, this is sine of x. Near the origin, the sine of x looks just like the line y equals x, just like it. All right. Now someone says, well, that's not near the origin. It is, because it's going to infinity, so the argument's going towards 0. So what I'm going to claim over here is that sine 1 over n, as n goes towards infinity, looks just like 1 over n as n goes to infinity. I'm going to say they look just like each other. All right, just like each other. All right, so what I'm going to do is, for comparison purposes, I'm going to compare this integral here. I'm sorry, I said integral, I didn't mean to say that. I'm going to compare this series here to this series, which I know is a divergent p-series. And I'm going to use the limit comparison test. Let me erase this thing over here. This is just my Math 120 talk about how they look. They're very similar looking. All right, let's put this down. And I'm going to write this down for you. So limit comparison test, right? So limit as n goes to infinity, sine 1 over n, and we're going to divide by 1 over n. That's like multiplying by n. I got to be honest with you, that looks like a really tough limit for me to do. So I want to kind of jog my memory back to Math 121. And I think in Math 121, you did this limit over here. You may not remember it though. And that was 1. And the teachers also said in Math 121, you did your homework, you had problems like this. Let me point this out to you. Well, typically you have a bunch of problems where the arguments were always going towards 0 at the same rate, and that rate ratio would be 1. Well, if you look at these things over here, both of these things over here are going to 0 at the same rate. So that limit's equal to 1. So let me look at this one over here, and I think it has something to do with that. So limit, if I want to say that, it's probably this one over here. So n goes to infinity, sine 1 over n, 1 over n. Same thing as that. What does this give me? 1. So what do I know? Let's go back over here. The limit's finite. This is divergent. This is divergent. All right. And they go through that work over here as well. All right, let's look at number 13. It says use one of the comparison tests. And again, my favorite comparison test at this point is the LCT. Now, before I do that, I want to point out its positive term series. I hope that's clear as day. All right. So I'm going to write this over here. And I'm going to use a series. I know I'm going to say not P series, it's geometric for comparison purposes, 1 over 2 to the n. This is a convergent geometric series. All right, let's go to town. LCT. What's LCT? Limit comparison test. Limit n goes to infinity. Let's write this down. 1 over 2n minus 1. We're going to divide by, 1 over 2n, which is like multiplying by 2n over 1. I'm going to do the limit, a little bit of writing, but not much. I'm going to divide top and bottom by 2 to the n, so I get 1 minus 1 over 2 to the n. And if you did that limit, you get 1. So it's a finite number. LCT says if this converges, this also converges. All right, let's go to the next page. See how we did. And yep, geometry is used for comparison. We got that. By the way, this is Deja Vu. Did I do 14 already? And there's a point to this, and I'll tell you what the point is. If you look at most of the tests you see at Essex, they typically be the same questions over and over again. Like when you do homework, it's going to look like Deja Vu all over again. I want to go back in the notes though, and I want to see if this question has been given to me because it sure does look familiar to me. But I'll be honest with you, everything looks familiar to me. I don't see it there. Number 10, isn't it? I'm going to copy this. And paste it in. I hope you agree it's the same question. Okay, so what's the point? This is the point. Your exams are going to look very much like what you see in class or in the homework. What does that mean? I would say attend all lectures, listen to what's being presented, study what's being presented, work the homework problems that are being presented to you and do the web assign if your teacher's asking you to do the web assign. All right. If you do that, passing courses should be easy peasy, lemon squeezy. Could you still make mistakes? Of course you can still make mistakes, but you're really gaming the system by doing what you're supposed to be doing. Now, this is a skill set that you should have learned a long time ago, but if you're learning it now, you know what? It's not a hurtful skill set to be learning. It's going to transfer well. I got to be honest with you though. If you're in a competitive market, like for example, let's say you're in a place where everyone is doing everything that they're expected to do. That's when the game gets up. That's when they start asking on exams questions you have not seen before. Now, I do this sometimes in my lower level classes. I give them questions that are similar but different. And for extra credit, by the way, just indicate students that they need to up their game if they're looking to be competitive. All right. Thank you for paying attention, though. And again, if you have any questions or concern, please bring it to my attention. This does require study, though. No one gets this in the first pass.